Introduction. The Earth Observation Satellite Planning, EOSP, tackles the complex task of scheduling observations for satellites that monitor our planet. This process involves selecting which observations to prioritize, given that there are many more requests than the satellite can handle within necessary time limits and movement restrictions. To make effective plans, it is essential to choose the observations that will yield the greatest benefits and then create a schedule that can accommodate these choices. Previous research largely relied on traditional methods for solving these problems, but this study introduces a new approach using advanced techniques called graph neural networks, GNNs, and deep reinforcement learning, DRL. GNNs help analyze and gather useful insights from the data, which is structured as graphs representing different scheduling scenarios. Meanwhile, DRL is used to help find the best possible schedules. The results of their simulations indicate that this new method learns successfully from smaller examples and can apply that knowledge to larger, real-world situations, offering strong results compared to older methods. The Earth Observation Satellite Planning Problem. The focus is on Earth observation satellites, EOS, that capture images of different locations on Earth to meet user demands. An agile EOS can target areas beyond the point directly below it, known as nadir. These satellites operate in low orbit, meaning they have a longer time frame for observing an area than the time it takes to take a picture. Adjusting the satellite's position for these observations involves changes in its orientation, known as pitch, yaw, and roll, which can cause delays depending on the specific observations and the duration of the transition. Typically, these satellites face a challenge known as the Earth Observation Satellite Planning Problem, EOSP. This problem arises because there are usually more requested observations than the satellite can complete during its operational time. Different observations might have different levels of importance or utility, making it necessary to choose the best mix of tasks to fulfill user needs effectively and create a schedule that respects the satellite's operational limits. The most complicated EOSP cases involve managing multiple satellites, each with different orbits and tasks, which may include taking many pictures of the same area at different times or using different satellites. Simplifying the scheduling problem. In this research, the analysis is limited to simpler scenarios involving one satellite operating in one orbit and taking single images, even though the scheduling problem is notoriously difficult to solve. This difficulty arises because, for many realistic situations with thousands of possible observations, finding the perfect schedule isn't feasible. Instead, researchers often look for approximate solutions using algorithms that provide good enough results rather than the best possible ones. A popular method for creating these solutions comes from a technique known as Greedy Randomized Adaptive Search Procedure, GRASP, alongside the emerging interest in using deep learning for optimization tasks. In particular, deep reinforcement learning, DRL, has shown promise in generating effective strategies for complex problems. Building on previous research that combined graph neural networks, GNN, and DRL to solve scheduling issues, this paper adjusts that approach specifically for the EOSP. The findings indicate that this new method offers significant improvements over currently existing techniques. The main contributions of this work include developing a new representation of the problem that doesn't break time into discrete parts, employing deep reinforcement learning for better problem solving, and leveraging graph representations as direct inputs for analysis. Graph representations and scheduling. The problem is approached by creating a large graph, referred to as a discrete graph, that represents the sequential decisions involved in the observations. In this graph, each potential observation is linked to specific starting times. Each point in this graph, called a node, shows a particular observation and its start time. For example, a node is labeled with an observation number and its start time within a specified range. Connections between nodes, called edges, indicate that one observation can directly follow another based on time constraints. These edges consider how long each observation takes and the necessary waiting periods before the next observation can start. Notably, there is a rule that prevents the same observation from being scheduled at two different times simultaneously. Some connections in the graph are removed for optimization. If another observation can be placed between two existing observations without violating time rules, the direct link between them is eliminated. This ensures that every time the two observations are included in a solution, the additional observation will also be part of it. To address the issue of the discrete graph becoming too large, a more compact representation, known as the continuous graph, was developed. This continuous graph only includes each observation once without specifying when it started. In this continuous graph, connections between nodes, representing observations, are based on whether there were connections in the original discrete graph. This method can result in two nodes being interconnected if the observations they represent can happen in any order. During each cycle of their algorithm, the system uses this compact continuous graph to decide which observation to prioritize next. To keep track of what choices are blocked by this decision and what options are still available, they update the discrete graph by marking the chosen observation as starting at the earliest possible time. Importantly, this adjustment in the discrete graph is reflected back in the continuous graph for the next cycle. Reinforcement learning approach. The approach used in this research focuses on creating an effective schedule for the EOSP by treating it as a reinforcement learning challenge. In reinforcement learning, the goal is to solve what is known as a Markov decision process, MDP, a model used for making decisions in a sequence of steps. An MDP consists of a set of states, possible actions, a way to describe how actions move us between states, and a method for determining rewards. In this case, the state is a specific scenario within the EOSP graph. It can either be the starting point, where no tasks are selected yet, or a later point with some tasks already in the schedule. The available actions depend on what has been selected last, allowing the addition of further tasks in a chronological manner. MDPs are great because they can manage uncertainty in decision-making. However, the researchers designed the EOSP scenario to be deterministic, meaning outcomes are predictable. When starting from a particular state and taking an action, the results lead to a specific next state without uncertainty. Each chosen action related to a task contributes a certain value, which is used as the reward in this model. The goal is to enhance the total rewards from these actions over time, building up a schedule that yields the best results. While the MDP setup is comprehensive, the researchers do not provide complete information about the state to the learning model. Instead of using the entire detailed graph, which could be overwhelming, they utilize a simplified version that doesn't capture everything perfectly, particularly regarding how long actions take. This leads to what is known as a partially observable MDP, where the incompleteness mainly involves estimated durations for tasks, which is not a major concern in the overall framework. Learning process and graph neural networks. In this research, the approach is based on reinforcement learning, where the system, referred to as the agent, is trained using graphs that represent partial schedules. The agent's task is to choose the next observations for scheduling and improve its performance based on rewards that measure how effective the schedules are. A simulator handles the different graphs and provides the necessary data to the learning agent. The agent works within a framework that maps states, which are the current conditions of the schedules, to actions, meaning the choices it can make for scheduling. The goal of this learning process is to create a policy that allows the agent to maximize rewards across a variety of real-world problems that are used to train it. Importantly, the agent needs to adapt well to new problems it hasn't encountered before, meaning it should perform well without additional training on unfamiliar instances. The architecture of the system involves several processing stages. Initially, the input graphs are transformed to enable efficient communication among different parts of the system. Then, simpler networks generate representations for the nodes and edges in the graphs. Following this, a specialized type of neural network called a message-passing graph neural network, MPGNN, is used to extract important features from the graphs and to calculate the likelihood of various actions being successful. Finally, the reinforcement learning algorithm adjusts the parameters of the whole system based on the rewards it receives, refining both the initial representations and the MPGNN. Implementation and evaluation. In this research, a form of reinforcement learning known as proximal policy optimization, PPO, is used, which is enhanced with action masking. One challenge involves the varying usefulness of different acquisitions, which can differ significantly, sometimes by as much as 8 times. Acquisitions are categorized into 7 priority groups, with usefulness scores ranging from just 1% to 10%. Within each priority group, the usefulness of an acquisition is determined primarily by that group's score and adjusted slightly based on predicted cloud cover. This adjustment encourages choices that are more likely to occur in clear weather. This situation can lead to inconsistencies when using deep reinforcement learning, DRL, as lower priority options may produce rewards that are hard to distinguish from random noise in the system. Furthermore, when training the learning model, low initial values are used that need to be improved, but small updates during training slow this process. To address these issues, various methods have been tried, such as using a logarithmic scale and a technique called too-hot encoding. Currently, an easier route is taken by dividing the reward received for each option by the average usefulness of all the available options. While this helps with the large value challenge, it does not fully resolve the discrepancies in rewards unless extreme priority classes are absent in the specific situation being analyzed. Further optimization strategies are being explored that consider important preferences. Experimental results and comparisons. The research discusses the implementation of a graph neural network, GNN, focusing on how nodes within a continuous graph are characterized. Each node is labeled based on the specific context of its observation, which includes details about the satellite's position during the observation. Although the graph does not convey the duration of transitions directly, the position information helps the GNN infer these durations well enough for effective learning, as demonstrated in simulations. The GNN uses a technique called graph rewiring to adjust how information flows within the graph. Typically, information would only travel in one direction, from past to present, but for this model, it's crucial to allow future information to influence current decisions. This is achieved by adding reverse links to the graph, enabling the model to understand both future and past influences. To build this graph, the model includes a graph embedder that enhances the graph by adding edges and using a multilayer perceptron, MLP, to process the attributes of the nodes and edges. This graph pooling technique creates a new node that connects with all existing nodes, allowing the model to capture a broader understanding of the entire graph, rather than just the individual nodes. When it comes to selecting actions based on the GNN's output values, the team concatenates values derived from all layers of the network. This process ensures that even though there are multiple layers, the final decision-making remains concise and straightforward, ultimately allowing for efficient action selection based on the available data. To adapt to various problem sizes, the model's design allows it to operate regardless of the number of nodes or actions. Each node corresponds to an action, so the learning process focuses on predicting the best action based on the reinforcement learning feedback loop. The proposed architecture relates seamlessly to a common approach called proximal policy optimization, PPO, but is tailored to ensure that the number of actions always matches the number of nodes, allowing for a more efficient and clear mapping between the two. Real-world application and further testing. In this research, a set of real-world problems was sourced from a company that operates Earth observation satellites. These challenges are represented using what are known as discrete time graphs, which are structures that show how different points, like tasks, are connected over time. The study uses a simulator to turn this discrete time information into a continuous time graph, which helps in processing the information over a continuous timeline. To illustrate the complexity of these problems, a table is presented detailing some statistics about specific test cases. The research compares a new approach based on deep reinforcement learning, DRL, to two existing methods for managing satellite operations. The first is the greedy algorithm, which is already in use. This method makes decisions by selecting tasks based solely on their immediate benefits, adding them to the operation schedule if possible. It may delay previously chosen tasks, but it won't cancel any of them. The second method is called ramp, which is a variation of the Dijkstra search algorithm applied to the discrete graph. While Dijkstra's method can find the best path through a network of nodes, ramp does not always lead to the optimal schedule due to some limitations in its design. This algorithm offers reliable schedules for actual problems but is too complex to be used for operations that require real-time responses. Thus, ramp serves as a benchmark for evaluating the effectiveness of the DRL approach in the simulations. In this section, the research compares its methods to existing approaches using a simpler version of the problem. The focus here is on maximizing the number of scheduled acquisitions without considering their importance or usefulness. To evaluate performance, 2 experiments were conducted. The first experiment was designed to assess whether the models and algorithms could perform well on a specific problem. For this, the system was trained on one problem involving a total of 106 acquisitions, allowing it to adjust as much as necessary to achieve high performance. The results showed that the system outperformed both the greedy method and another method called ramp, indicating that the architecture can effectively implement strong strategies. The second experiment aimed to test the system's ability to apply what it has learned to new tasks. In this phase, the model was trained on 128 problems, each with about 100 acquisitions, and tested on 31 new problems of similar size that it hadn't seen before. The learning curve from this experiment demonstrates how the system's performance improves as it learns. Additionally, the research checked how often the system outperformed or matched the performance of both the greedy method and ramp on the new problems. The results indicated that the system can successfully adapt to new challenges and surpass the currently used solutions. In the second round of experiments, the focus shifted to understanding the usefulness of different observations to maximize the overall benefits in the final schedule, similar to a well-established decision-making framework. The team conducted 2 sets of tests, one where the system concentrated on solving just one problem to achieve optimal performance, and another that examined how well the system could adapt to new, unseen challenges. When testing on a single problem involving 88 potential solutions, the system demonstrated that it could outperform a more straightforward approach called the greedy algorithm, achieving a particularly high score known as ramp. This result suggests that the system's design is well suited for tackling complex decision-making tasks. In terms of generalization, the system was trained on a set of 639 distinct problems, each involving about 100 potential solutions. It was then evaluated on 27 new problems of similar complexity. The results indicated that the system could effectively apply what it learned, as shown by the learning curves. Moreover, when comparing its performance to the greedy strategy in ramp using various test problems, it became evident that the system, referred to as Wheatley, consistently performed better than the existing solutions and approached the best possible results. Conclusion and future directions. The research shows that deep learning methods are beginning to challenge some of the best-known techniques for solving the effective observation scheduling problem, EOSP. The team is exploring various ways to build on this work. One approach involves using specialized algorithms that prioritize tasks based on their importance, which could help in creating a more effective schedule. Currently, the team organizes tasks in the order they are added, following a chronological sequence based on predictions made by a graph neural network, GNN. However, the effectiveness of this method is limited by how many layers the GNN has, restricting its foresight. To improve this, future efforts will focus on developing a different way to represent the EOSP using a continuous time graph. This new representation would allow for more flexibility, enabling tasks to be scheduled in any order. This change could lead to enhanced strategies that take into account varying levels of importance for different tasks.